some people can join us from online via Zoom link, right? Because it still never starts.
No, it
starts?
Mm-hmm.
No, it doesn't. Okay, now it started. Okay, good.
No, now we're there.
Right. But then we have audience also here in real life. Good. So my apologies, big apologies for the technical troubles. So we are starting a bit later. Okay, 9 minutes later than planned, but luckily many of you stayed here. And now you have Zoom link, so you can even join us and talk to us in real time, right? So that's even better, I guess. So let me share my screen now and welcome everyone to this broadcast. First of all, I want to show that we promised that we'll deliver you surface hopping dynamics with MLatom, and it should support Python API, different machine learning and quantum mechanical methods. And it was here, MLatom is coming. So now it has already come. We just released it 1 hour ago. You can download it using pip install or go to the GitHub, download the source code. And we are joined today with our guest star, Mario Barbati, who introduced me to the field of surface hopping dynamics. And now my group too. And also Joanna, who is a specialist in surface hopping dynamics, and we are joined by our group members, students from my group, John Lina, who developed this surface hopping dynamics in MLatom, and also from Jana's group, Mikolai, who is using these methods, and many other people who contributed to this release. So what do we do here is that MLatom allows you the whole workflow from geometry optimizations to normal mode calculations. Then you can generate initial conditions, run surface hopping dynamics, and prepare population dynamics, all in one script, basically Python script, which is not too long. And this becomes possible because we also use parts of MLatom XACS. So Mario can elaborate on this more. So we are heavily using and relying on expertise of MLatom XACS developers team. And to get this particular version to run in Python, so you can do pip install MLatom, or you can, if you already have MLatom, you just run pip upgrade MLatom, and then you'll get it. We also have XACS Cloud Computing, where you can perform the simulations. I will show you examples. And the big versatility and the big advantage of MLatom is that you can do it with many different models. I will show you later these models, but for example, you can just define them through Python interface, and then you can use these models to do like everything from geometry optimizations to non-empathic dynamics as shown here. And these models, there are really a big variety of these models. So they range from quantum mechanical methods that you're used to pure machine learning methods that you can train for your own models and using for your own systems and for your own data. And we also provide some pre-trained solutions, and such as AIKM1, which we'll show some results with. These, which are highlighted in red, can be used to run excited state simulations either out of the box in case of methods, so-called methods, or in case of machine learning models, you can train them on your data. How to train, it's another topic. So we'll just show how to use the existing models. And now is basically, that is for very short introduction of what we released, and I will show you in the real time how to use it. So we'll go to the XACS Cloud Computing on xacscloud.com, and I will share my screen again. So this is done. This is done very easily if you go to xacscloud.com here. And okay, so now you can see the screen. I see it also on YouTube. So this is a website. And then when you click on cloud computing, you would need to register first, of course, with your real information, and this for free for academic users. And then when you connect to Jupyter Lab, you can run the simulations in your Jupyter notebook. So you click on connect, and then you can find some tutorial materials already pre-uploaded for you in your folders. And here we'll go through quickly how to do it. So basically, I will start this calculation. So this is a quite short notebook. So it's not very long. So you'll just click to start all the calculations from scratch. What it does, it loads MLatom. Then it downloads initial conditions from some database, which we already prepared for you. And here on specific example of machine learning models, so we need to some class which will load the machine learning models and use them later. But if you use some kind of quantum mechanical method, it's even easier. You can just specify like this AIQ1. And then you say, okay, we use these models, and you need to specify requirements for your dynamics. So here 5 femtoseconds maximum propagation time, 0.25 femtoseconds time step for 5 steps, for 5 electronic states. And then you run dynamics here in parallel. So we don't need to wait and submit them separately. So you run these dynamics, and then you see they already finished actually. So they finished faster than I was talking. And then you dump these trajectories. You can analyze them later in JSON format, in H5MD format. You can dump them also in XYZ format. And then you can analyze trajectories here and then plot the populations. So in this particular example, it was faster than I was talking. Of course, if you use something like quantum mechanical methods, it will be much, much slower. And here, I want to emphasize that this is work of many people, and we also tested these implementations. And in the next, I will basically stop sharing, and Lina can show what did she do? So what kind of surface hopping dynamics she implemented, and which one is supported now currently? A bit about theory, and show some results which we obtained with this implementation. So Lina, could you please share the screen? I need to.
Sure.
Okay. Yes. Yep, I did. Mm-hmm.
Okay, I'm now sharing my screen.
Yeah.
Okay, can you see it?
Yes. Okay, now we can see it.
Yeah. Okay, basically, the surface hopping dynamics in MLatom is based on this Landau-Zinner. Okay, let's switch. Yeah, Bayev-Lebdev formula. And actually, previously, we know this Landau-Zinner formula. It is conventional, and it is in a diabatic representation. So if we use this original Landau-Zinner formula, actually, it is not that easy to run surface hopping dynamics. But then in this paper, Bayev and Lebdev, they rewrote this original Landau-Zinner formula, make it to be in a adiabatic representation. So basically, in this new formula, they just need the energy gap between the adiabatic states and also the second order time derivative of this gap. So it is very easy to be used in surface hopping dynamics. So basically in MLatom, we use this kind of a simple formula to run Landau-Zinner surface hopping. So actually this kind of formula has many advantages and also disadvantages. So advantages is that the lack of the coherence problem of FSH method does not arise in this approach. And most importantly, this formula is very efficient because we don't need to calculate the non-adiabatic coupling vectors. So because this formula is just based on the information of potential energy surfaces. So based on this reason, actually a lot of different electronic structure methods can be used. like all of these methods that they don't provide NUCs, we can use all of these methods to run surface hopping dynamics. And it also has some disadvantages, like classically forbidden transitions cannot be treated. And then here I show some results that we use this LZBL formula for surface hopping. And the first example is the CH4+. So on the left, we show this CASSF result, and we check the literature, and it has good agreement with the literature population. And we also run the surface hopping dynamics using AIKM1, and AIKM1 is kind of unique method in MLatom. And we use AIKM1 with the multi-reference CISD. And you can see that actually this AIKM1 result has good agreement with the CASSF. Although it is not that perfect, but the shape is basically the same. And then the next example is about Parison. So for Parison, we use ADC2 CSPVDZ to run surface hopping. And yeah, it is based on this Landolt formula. And also it has good agreement with the literature population. And then we also, for this molecule, we use AIKM1 to run dynamics, but this time we use just the CIS. We can see that basically they have agreement qualitatively, and basically we kind of can use AIKM1 to reproduce the population very fast. Yeah, that is all of this introduction and the results. Thank you.
Yeah, so thank you, Lina. I think Mikolai can actually show some. Mikolai can actually show some results.
Yes. So I should share my screen now.
And in the meantime, maybe Mario can comment how he likes this approach, because Mario really implemented very nice approach.
Hey,
right?
Can you see my screen?
Yes. Yes.
Okay. So I would like to talk a bit more about the applications of Landau-Zenner surface hopping as implemented in MLatom, as I am doing quite a bit of trajectory surface hopping simulation as part of my PhD thesis. And the kind of first example that came to my mind when trying to showcase this method is it's a very classical example in photochemistry, and it's the isomerization of azobenzene. Isomerization of trans-azobenzene after optical excitation to the first excited state, which is an n-pi star transition. So it's a common example when you are trying to showcase a new method. And before I show the results, I would like to show like a bit of the code that I used for doing that. So I know that after this update, this may already be detracted. The actual code may look a bit different, but I would just like to highlight the fact that unlike, for example, the MNDO program, running simulations in MLatom is extremely easy. You can just write about 15 lines of code, and it gives you all the results that you need. It's also very easy to modify and handle if you want to do it yourself in any way. And now for some of the results, I ran the trajectories of azobenzene with three methods: ODM2 MICISD with Landau-Zenner surface hopping, ODM2 MICISD with AIQM1 correction, also with Landau-Zenner surface hopping, and as a benchmark, ODM2 MICISD with fewest switches surface hopping propagations. And we can see, if we look at the plot of how the ground state population increases in time, we can see that all those three methods give qualitatively pretty much the same results. However, if we look at the simulated quantum yields as predicted by each of these methods, we can see that remarkably here, AIQM1 gives a much better result. It gives an isomerization quantum yield that is in good agreement with experimental data, while all the semi-empirical methods, the same semi-empirical methods, but without the machine learning correction, predict a qualitatively completely wrong result. So yeah, that's the azobenzene, and then as the last part, I would like to show something related to my PhD thesis, which is non-adiabatic dynamics of a polarized molecular wire. And this is kind of the class of systems that I am investigating as part of my PhD thesis, which are very large molecules that can, after absorbing UV light, perform spontaneous charge carrier separation. And those systems are particularly challenging for simulating the non-adiabatic molecular dynamics because they are very large. This one here is about 80 atoms, including, if I'm not mistaken, 50 heavy atoms. So it is simulating this with full fewer switches surface hopping and computing the non-adiabatic couplings. It takes days to run a single trajectory. So here I was able to successfully propagate the dynamics using Randall-Zener surface hopping at different levels of theory, using AIQM1, using ODM2 CIS. And when comparing the Randall-Zener results with fewer switches surface hopping, I think the qualitative agreement is quite good. And especially with AIQM1, it can give very reasonable results at a quite low price, low computational cost. So that is all from me. Thank you very much.
All right, so thank you. I mean, we can give some concluding remarks, maybe from Mario, what he thinks about it, and Tiana. What are the plans?
Hi, people. Mario here. Yeah, I'm very happy to see and glad to see such a results. I mean, I think there's a lot of space for this kind of semi-quantitative results that can get very fast to get an intuition about how your system performs. I don't think that at the end we are going to get final quantitative results, but what you get in a very good way are the you explore the configurational space to discover what are the important reaction pathways. That's what this kind of dynamics is doing very quickly. And then afterward, you can use some high-level method like SPT2, for instance, to check the reaction pathways using static method, not dynamics anymore. But these initial dynamics, very fast, very exploratory, is essential. And I have no doubt that's a good way of using both ways. One, AIQM1, or ODM, one of those very inexpensive electronic structure methods, and on the other hand, using Randall-Zener-like couplings that has a few drawbacks, but in general they perform very well. So happy to see those results.
Yeah, thank you, Mario. So, Jana, in your experience?
Well, from my experience, mostly as a user, I would say that this combination, so machine learning corrections and the Randall-Zener dynamics, really expands the scope of systems that we can tackle with the dynamics method. So for us, this is particularly interesting as we are now in the group really focusing on a little bit larger systems for electronics. So this is like a new method that we are really glad to have, and we will be really happy to try. So far, the results look good, and I'm looking forward to more development, definitely.
Okay, thank you very much. So with this, we just want to emphasize that this is just the beginning. So we will later also release many more upgrades, including active learning to get robust potentials. Also for excited state dynamics. So subscribe to our channel. There will be also in the description to the video, and the documentation and tutorials, the links to them will be also all there. So thank you very much, and hope to see you around.